Very good. Let's resume where we left off. So as a brief reminder, we've brought ourselves into the situation that we're considering how to use machine learning to work with low-level representations of data in the hope that we can get more out of it. And after a relatively lengthy introduction, we came to the point where we were considering the first and very popular approach of representing data, and this was to map this colorimeter deposits into an image. And we left off at this image where we discussed a bit how these images are constructed, but the key point was that we are indeed able to see that these chat images carry physics information that should be relevant for the classification task. And now the question is, how can we use machine learning to deal with this? And so let's first think what we want an architecture that works with image-like data. What properties do we want that to have? And there are two key properties that are implicit when we represent data as an image that the chat images to some degree also not perfectly fulfill, but this should always be in your mind when working with image-like data. And these two things are locality and translation invariance. Locality means that if we have a photograph of some scenery, then pixels that are close by each other in the image should share some amount of relevance. So for example, if you take a picture of a cat, most of the pixel that belongs to a cat will be close to each other. Most physical objects in this sense are compact. So we need to find a way to encode this information that nearby input pixels represent objects or should be treated together into a neural network architecture. And secondly, we have this property of translation invariance. Again, this is more true if you think of classical photographs. If you're trying to identify the presence of a cat in your photograph, you don't care if the cat is in the top right corner or the bottom left corner of your image. You just want to know, is there a cat in my image or not? If you're thinking with me, then you already realize that the chat images, due to the pre-processing that we do, so due to this rotation, mirroring, and so on, these images actually are not necessarily invariant under these translation symmetries. So we have a very specific subclass of images where this maybe doesn't fully help or is not fully exploited, but in general, these are the properties that are encoded by a convolutional architecture. Some specific problem that you might care about might fulfill these assumptions to a larger or to a lesser degree, and depending on that, it might work better or worse. But in principle, if we can project data into an image, we can work with this. And now I come to an interesting point, because this is some results or some discussion that I usually do on the Blackboard, but since here the setup is rather separate between Blackboard and Presenter, I put my Blackboard notes on the slides. This will maybe be a bit bigger than if I draw everything live. On the other hand, it's also large enough that you can read it, and my handwriting is not as good as David's, so I think this is maybe a good compromise. So let's first start with the question how we go from the data that we have and what it means to represent this as an image. So the simplest thing that you could imagine is that we have this 4 × 4 pixel image here that is just black and white. So either a pixel is on or off. I indicated this in this very artful drawing over here. And of course, it's a very small conceptual step to say a 4 × 4 pixel image that is just black and white pixels we can represent as a 2-dimensional binary matrix. So this is a 4 × 4 matrix. We put a 1 wherever we had a pixel that was black. We put a 0 wherever we had a pixel that was white. So this is, let's say, the simple conceptual step that allows us to go from an image to a matrix representation that we can use as an input for machine learning algorithms. And I'm sorry, I know this is a room full of smart people, and for many of you this might be a trivial step, but it's useful to at least once say it explicitly that this is what we're doing. So we're translating this image into a pixel representation as a matrix of numbers. So if we had a set of features, so some high-level observables, it would be individual xi elements, some space r or some rd. We would write this down as a vector. Whenever we talk images, we get matrices. And if we have a black and white image, we have a matrix with 2 indices. So the individual pixels are either a 1 or a 0 coming from enters in time. So this gives us a matrix with 2 indices that we can call k and l. If we have grayscale images, so not just a 0 or a 1, but gradients in between, we can also represent this as simply as that with the matrix. But now, instead of taking 0 or 1 from the set, now if we have a grayscale image, the individual xi are elements of this range between 0 and 1. Of course, the overall normalization is arbitrary, but we can pick a normalization where a 0 corresponds to a white pixel, a 1 corresponds to a black pixel, and we interpolate everything between. So again, this is represented most easily as a matrix with 2 indices. What is usually done in image processing outside of physics, if you think of the photograph that you're taking with your camera, of course we don't have grayscale images, we have color images. So a color image would be, again, a range between 0 and 1, but for each pixel we actually store 3 values. And in this color image, these 3 values could be the colors red, green, and blue, or whatever decomposition the specific representation of the image is using. But we can think of color images in the input range starting with 3 colors. And this would correspond to a representation of the data as a matrix with 3 indices, C, K, and L in this case. Now, let's put a mental bookmark in the topic of colors. And if I try to leave the topic of convolutions without talking more about colors, please stop me. I don't have a specific slides on it, but there are a few more things I want to say about it. So we'll come back to the topic of colors, but for now we can start with grayscale images. So we want to represent our chat data, and we want to work with a convolutional network. And the simplest possible thing, if we were having a chat image and wanted to process it with a neural network, would be to flatten it. So we can take the 4 times 4 matrix, and we can just say, okay, we take the first row of the matrix, that's the first 4 pixels. Then we take the second row of the matrix and put it next to it. Then we take the third row of the matrix, put it next to it, and then we take the 4th row of the matrix and put it next to it. So again, this is a very trivial operation, but whenever we have data represented as a matrix, we can always, in a unique way, or there are a few choices, but of course this is invertible, we can always represent that matrix also just as a vector of elements. But what we're losing if we turn a matrix into such a flat vector, we're exactly losing one step back. If we turn this matrix into just a vector of 16 elements, you could say, okay, now I just have a list of high-level features. Or it's not high-level, but it's just a list of features. It's just a vector of features. Now I could use a fully connected network on this list representation of the matrix. This is perfectly technically possible, and actually a few of the earliest applications of chat images to machine learning and chat physics exactly did this way. So you could do that and just say, okay, each of these is the input nodes to a fully connected network. There is a big problem if we want to do that. The big problem is that if we just write down the fully connected network as we've seen before, we have random weights connecting each of these inputs to the nodes in the latent space. And if we do this, we've completely lost the information that this pixel here and this pixel here in the next row are actually geometrically close to each other. In principle, the network could learn it, because if we show it many images, it could again learn that this pixel has more to do with that pixel than with this pixel down here. But we've lost this information for now. So while it's technically always possible to represent as an image as a vector and use a fully connected network, it's missing an important aspect of the problem. So what could we do? And of course, things like a fully connected network, this is another important point here, a fully connected network cares about specific features. So for example, if I change the value in this feature, or if I have a specific value in this second node here, in the classical approach, this might be something like the mass, and over here I would have the n-sub-jettiness, then it makes a big difference if a value is here or here. In an image, if I just have a cluster of 4 cells and I move it to a different place in the image, and I said I would like to have the algorithm to be translationally invariant, this would not matter. So a fully connected network explicitly, in a sense, breaks translational invariance, because in this way all the input nodes have a different property, and it is very difficult to recover, to learn this property from the data once you've broken it in your architecture. So I hope I've convinced you that treating an image with a fully connected network is not what we want to do. And the answer to how we can treat image data in a way that respects the actual symmetries of the data is convolution. So we're looking here at the 2-dimensional image with one color. So this is a grayscale image, and it just filled this matrix with a couple of random numbers. So it's numbers between 0 and 1, 0, 0, 1, 0.5, and so on. And you can imagine that this image extends, well, if we have a 1,000 times 1,000 pixel image, we draw the first 4, so this extends 996 pixels more to the right here. It just gets too big to draw. But for everything we want to understand, just looking at the small corner of the image is perfectly sufficient. And the key element of the convolution operation is this convolving or folding the input matrix with a second matrix that is called a convolutional kernel, or in the image processing language is also called a convolutional filter. So how does this convolution operation work? Well, you can literally think of applying this matrix to a certain region of the input image. So we start in the top left corner, and we take the scalar product of this section of the matrix with this image. So we get 0 times 1 plus 0 times minus 1 plus 0.5 times 0 plus 0.2 times 0.5. So the result, that was a 0, that was a 0, that was a 0. So the result is 0.2 times 0.5 gives us 0.1. So we put 0.1 in the top left corner because we started in the top left corner here. There's a few subtleties. I'll come to them in a moment. But for now, we just start in the top left corner. And we move, after each of these applications, we move this convolutional kernel by 1 pixel to the right. And once we're at the end of the image, we move it 1 row down. So what this does, I'll just do a second calculation, and then I think you have figured it out. So we start in the second position, 0 times 1 plus 1 times minus 1, so we stand at minus 1, plus 0.2 times 0, we still stand at minus 1, plus 1 times 0.5, minus 1 plus 0.5 is minus 0.5, so this is the minus 0.5 here in the second element. So as I said, we just take the input image represented as a set, as a matrix of real numbers, and we multiply it with the convolutional kernel that extracts some features. So you might be confused, what does this have to do with machine learning? And we get there in a moment. We're just building the operations we need to do that. So we figured out how to apply a convolutional filter to the image. And the first observation that we have is that this convolutional filter, indeed, no matter where in the image we apply it, if it is sensitive to a specific pattern, it will show up as a specific number in the output. So we have this property of translation equivariance, so that the filter does not care where it was applied. The second property that we have is the property of locality, because quite explicitly, this filter only looks at the specific local neighborhood in the image. It considers a bunch of pixels in the local region and produces one output that, in a sense, summarizes the properties of this region. Okay, very good. So we've done this convolutional operation to this grayscale image. Just for completeness, I've write down the equation how you can do that. So this is a double sum over essentially the horizontal and the vertical dimension of the filter, and we do the convolution of this kernel with the local region in the input image. Now let's convince ourselves that these filters are doing something useful. So let's imagine we have listed here a couple of filters. And the nicest example is the image up here. So imagine we have an image that consists of two colored bands. We have 0 was 1 and white was black. So essentially we have a white band up here and a black band down here. This is some image that we have in our input data. And now we can imagine how a filter would actually find a specific property. So you can think of this horizontal filter here. If we have a row of 1, a row of zeros, and a row of -1s. If you apply this filter in a region of the image, like up here, where all the numbers are the same, then we have something that is constant. Then we have, well, 1 times 0 times 3 still is 0, and -1 times 0 is still 0. If we apply it in the region where everything is 1, well, this gives 3, -3 is still 0. So in the regions of the image where the color is constant, this filter just returns a 0. If we apply this filter to a region of the image where there is a color change, so if we go from up here to down here, then the +1s and the -1s will see different parts of the image. So these contributions will not exactly cancel anymore. And what this does, it gives us a couple of -3s in the middle of the image. I'm not sure if I did the calculation here correctly, but there's at least one row of -3 happening here in the middle if we go from the zeros to the from between the zeros and the -1. So you can imagine you're in the middle here, and then you have the top row that is multiplied with zeros. The bottom row is 1s minus -1, so you have -3s here in the bottom row. So now we've built ourselves an edge detector just by picking a few smart values to put in the specific places of this kernel. We've found something that whenever you have an image, it tells us there was a horizontal edge in that image. It tells us that there's a change in the color. Very similarly, of course, you can also build a vertical edge detector. You can combine this to find the vertical edge and the horizontal edge at the same time, and there's a number of other filters. These filters applied to images are, of course, again, much older than machine learning. But classically, what people would do is come up with this type of filters. The big change, as we're now turning this into a machine learning application, is to say, okay, I don't want to think of the values here in the filter myself. What we do if we learn a convolutional network for image classification is we structure the architecture in such a way that the trainable parameters, the weights of the network, are these numbers in the filter here. So very concretely, when we train a convolutional network, we optimize a set of filters that is optimal for the specific problem that we want to do, in the same way that we've now thought of, as horizontal, if we want to find the edge, I can do a horizontal filter. If we do it with a convolutional network, if we do it with a neural network, we just put the weights here in the different parts of the network and set up the calculation in such a way that we can do backpropagation and gradient to find the optimal values of these parameters in the filter. So conceptually, this is still a convolutional network with the big difference that we don't need to come up with the filters ourselves anymore. It's an important statement, so it's here in the black box in the convolutional architecture. The weights of the network are the values of the filter. Very briefly, this is a bit more technical, but I think it's important to at least point it out once, because it's a common topic to get confused about if you want to apply it to a concrete problem, as you're going to do today in the exercise. If we do a convolutional architecture, there are two important rules. One layer in the filter per input color. So the if we apply the filter just to a two-dimensional image, the filter is just a two-dimensional matrix. If we apply the filter to a three-dimensional, if we apply the filter to a three-dimensional image, also the dimensionality of the filter needs to grow. So if it's a three-dimensional image or an image with multiple colors, to be more exact. So if we apply the filter to an image with 3 colors, we need a red filter, a green filter, and a blue filter, very simply. So for each color in an input image, we need to have one additional layer in the filter that we sum over. And if we apply now such a unit, We could, of course, just apply one filter. We could also apply multiple filters in parallel, randomly initialize all of these filters with random numbers, and then let the network learn a family of filters that together will solve the problem. This is what convolutional networks do. We never just learn one filter, we learn tens or hundreds of filters simultaneously. And you can think of conceptually at each individual filter that you apply to an input image yields a color in the output image. Of course, calling this a color is approximately as justified as calling the things, as calling the charge that the quarks and gluons have a color. It's a nice analogy because in some way it behaves like a color, but of course, if you train a neural network with 100 filters in the first layer, it does not mean that the output image has 100 colors in any sensible way. It's just treated the same way as we treat red, green, and blue layers in an input image algorithmically. But these two things are important to keep in mind if you design more complex things. The other really nice observation we can make about convolutional filters is that we've now found something. Let's look back here. Or we can stay here. If we're processing an input image with 1,600 pixels, 40 times 40 pixels, and we were to process that in any reasonable way with a fully connected network, and we say we have 10 nodes in the second layer of the network, with a fully connected network, this would mean 1,600 times 10, so 1,600 connections. This scales very badly with the size of the image. If we apply one input filter to the image, and we say it's a 3 times 3 filter we apply to the input image, the 3 times 3 filter has 9 numbers as free parameters. So we process the input image not with something that has 16,000 trainable parameters, but that has 9 trainable parameters. Okay, maybe we don't do one filter only, but we do 10 filter. Okay, we have 90 trainable parameters instead of 16,000. You see, it scales much more efficiently, and the reason it can do that is that we're using the symmetry property of only learning weights that are looking at a specific geometrical region, and that we're sharing the weights for all the positions. So this is buying us a lot of efficiency in terms of the network. Of course, we need to validate for ourselves that this much simpler architecture in terms of the number of trainable parameters still has the same performance if applied to a practical problem, so that it has the same capacity. But you will see in the exercise that it does. Okay, so we see how we built this image. Let's see how we take this and turn it into a convolutional network. So I already said, you can think of one convolutional layer as the application of one of these filters. And in a practical application, you do three things. First, you can apply several convolution layers after the other, typically with multiple filters in parallel. So in this case, as I said, feature and kernel and filter are equivalent terms. So in this case, we apply 4 times 4 pixel large convolutional kernel to the input image, and we apply 8 of these kernels in parallel. So we get out of one image with one color, we get one image with 8 colors in this example. The second thing we can do, in addition to applying convolutions, is another operation that is called pooling. So a convolution is a multiplication with this filter matrix. Pooling is a downsizing of the spatial resolution of an image. This means I, for example, take the mean, this is called average pooling, or the maximum, this is called maximum pooling, of a 2 times 2 or of a 4 times 4 region of cells. So I say, okay, I want to reduce the spatial resolution of my image by just taking the average over here, taking the average over here, taking the average over here. It's very, the simplest way of reducing the size of an image that you could do. This is called pooling, and traditional convolutional architecture consists of these two things. So we start with convolutions. These convolutions you can think of learn abstract features in the data. So we learn more and more properties that describe the image more globally, and at the same time we reduce the spatial resolution. So learning features, reducing the spatial resolution. You can do this one time, you can do this a couple of times, and at the end, what we have here as the output of the last layer of these convolutions, These are, in a sense, high-level features. So what the network has done for us is that this convolutional chain has acted as what we can call a feature extractor. So it learned useful features to describe the data, and it learned these useful features by building these filters that filter out specific properties of the parts of the image. And you already know what to do. If you have something that is a high-level feature representation of your data, you throw it into a fully connected network. And when training a convolutional network, of course, one trains these things jointly, but conceptually, you can really think of first something that processes the data in image space to learn some high-level features, and then something that does the remaining analysis with these high-level features until it gives you the output. And many of the architectures we're going to talk about today have exactly the structure, that this has something that lives in the, let's say, more interesting abstract space, and then just a fully connected network in the end to give you the final output. I had an exercise, David gave homework exercises, so I think I can offer one homework exercise myself. This architecture diagram is from our first paper on deep learning we've written together with Tillman, Anya, and some students, this reference here. And you can read it, and you can try to find all the mistakes we made. David already did the homework. They published another paper. I think you found 7 stupid things we did. There are probably 1 or 2 more. So this is a nice exercise, reading a machine learning and physics paper from 2017 and see how many stupid things we did back then. It shows that the field is progressing very rapidly. Okay, so we've put this together. Let's briefly look at some visualization, not done by us, but I found this very nice page. So what we have here, I'll sit down for that, sorry. What we have here is, and let me maximize my window so you don't get distracted by my many desktop items. What we have here is first a fully connected network trained on the MNIST dataset. You might have heard of the MNIST dataset, or you might not have heard of it. It's a dataset of 28 times 28 pixel images. If somebody counts quicker than I do, please don't correct me. It's something of that order of magnitude, of handwritten digits. And this is one of the classical machine learning exercise datasets. And essentially, it's a multi-class classification problem with 10 different classes, trying to classify the handwritten digit into the class it belongs to. And what we have here is a fully connected network that takes this input, flattens it, and then has 2 hidden layers to try to give the prediction score. And what we can do here, I can hand draw a number. So let's see, let's draw the number 3. And it has these pixel activations, and then you can hover with your mouse cursor and see which of these pixels contribute to the cell. And you can see, as we said, the fully connected architecture is not very efficient in its weight. So all the pixels contribute to each of these cells here. So you have all these lines from 32 times 32 or 28 times 28 to 1 pixel, and it's a fully connected architecture. So if we then want to know how we go here, you see that all these other pixels again contribute to this 1 pixel, and in the end, it gives the correct answer 3, but it receives the input from all of them. So this is, you see, for such a simple task as classifying MNIST digits, of course, also a fully connected network works fine, but you already see this property that I was talking about with the connections, and you can see a bit. So the colors represent the activations, and the colorful lines represent how much each of these input contributes here. So what we can also do is we can look at the convolutional network. Yeah?
What happens if you write like a Q or something? Your Q looks like a Q.
Sorry?
Okay.
Oh, a Q, sorry. Let me do a psi, that's easier to draw for me. So it thinks it's a 3 or a 7. Okay, it just gives you, well, it gives you activations if you had access to the, we have access. So it has a 0.3, I mean, we can look at the numerical score. It says it's 0.34% certain that it's a 7. If I draw an actual 7, it's 0.37, so it's a bit higher. So as we said, I mean, this is a fully connected network on MNIST data. This is not doing great. we can do the same thing, but now use, I wanted to switch to the other tab. Now visualize how a convolutional network works. So let's draw the number 5 now. That's a very nice 5. So you see, now the intermediate representations of the data are much more expressive. So this is, again, this is the layer after the first convolution. So you can think of the network applying a filter. And I think this is, I mean, you see it. If we just go to one specific position, and actually I'll hover here and then explain it, the arrow. So you can see to produce this pixel, we actually have only this local region. So I think it's a 4x4 or a 5x5 filter applied here. So only this local region gives the input to that one. So this means there is a much smaller input region for each specific pixel. And the way the convolutional network becomes sensitive to the whole image is that we compress down and down in geometric space, and you see that from very concrete representations, where is still the 5, this turns into more and more abstract feature maps that encode something like, for example, these typical belly hole that the 5 has, and so on. So these shapes that are learned here in the abstract way. And in the end, we've completely lost the connection to geometry, and we're just in this abstract space. But you see first how essentially the image gets digested by the network. It's a nice tool to play around with there, but we can actually repeat the exercise. So if I now draw my very nice psi here, it gets still picked up, but now it's an 8. It's fairly certain that this is an 8. Okay, it hasn't seen enough Greek letters to be sure that I'm drawing something that should not be a number. Okay, let's jump back to the presentation. We're still sharing on Zoom. Very good. And let's take a break here and see if there are questions on convolutions. All clear? Or people need to have a second to digest this? Okay. Then let's move on. And we next cover something called the recurrent analysis of the clustering tree. And I'll just try to motivate it first. So there is a downside to the chat images. And the downside to the chat images is that you've actually seen this. We can actually play it again. So if I show you that image here, who wants to guess what the downsides could be? Why is there a potential problem waiting for us? Wild guesses. Yeah, you know the answer. Wild guesses by people who are not preparing the tutorial. What could the problem of this image be? Sorry? Translation. Okay, so you correctly spotted indeed this is not translationally invariant, but it turns out that convolution works reasonably well even if we don't use the full symmetry space. So this is fine. What else could it be? What don't you like about this image? Does this image look like a photograph to you? If you take a photograph with your camera of this room, what's the key difference between that photograph and this image? Yes? Very good. This is called sparsity. So this image is basically empty. Most of the cells are 0, and a couple of the cells are a number different from 0. If you're thinking about image processing with photographs, unless you're taking pictures of a candle in a dark room, most of your pixels actually will have some interesting value. So sparsity is bad because of 2 reasons. The first one is that it's an inefficient way to store and look at our data. And it's acceptable if we do chat images with the resolution that corresponds to the colorimeter. If we wanted to do an analysis with a spatial resolution that corresponds to the power of a modern tracking detector, we would need an image with much higher resolution. Much higher resolution would mean even more sparsity and even more waste of space. So there is a certain limit up to which images can represent the actual resolution of the detector. The second issue is that learning of convolutional networks becomes less efficient if most of the pixels are zeros, because you just have much fewer positions where you're actually generating useful gradients for your learning. So that's bad. So what we started doing is essentially we found an exciting tool from outside of physics, and we played with it, and we realized it works, but it's not properly representing the properties of our data. So what else could we do? And the second thing that's also not physics, but that people outside of physics like to work on a lot, is the processing of natural languages. Why? Well, we can first look at this analogy. So we can think if we have a text, and we want to process this text word by word or letter by letter. I copied here a Korean poem from Wikipedia. I hope it's not something inappropriate. But if you had a machine learning algorithm, you would analyze this, and now you need to shout at me if I'm going the wrong direction, but I think you read left to right, right? Right to left. Left to right, good. So you would process this really having a network that looks at this first character, looks at the second character, and so on, and then tries to make some prediction about the content of that poem, for example. Or in general, a big application of language processing is translation between different languages. So you might want to have a network that goes character by character through this poem and translate it to German, so I can also appreciate it. How can we translate, pun intended, this type of application to something we are interested in particle physics? Well, we could say our 4 vectors, the decay products of the top quark, are a list of items that is ordered because we can sort it, for example, by their transverse momentum. So we can sort this list of items, and this has the big advantage that we can use the input data at the full resolution, at the full spatial resolution, because we don't need to turn it into a pixelized grid anymore, and we can directly work with the 4-vector data and consider it as a sequence. So again, if we make this analogy, then one sentence or one poem would correspond to a chat, and one character here would correspond to one 4-vector. And luckily, there is quite an active area of research also for the processing of text-based data, and the big template that is being applied to that goes by the name of recurrent networks. Recurrent networks, they're called this way because a network block is again and again applied to the different inputs. I'll talk about the structure more in a moment, but I just want to make a brief aside. Everything we've talked about so far were indeed feed-forward networks because the information only flows one way. With the recurrent network, we actually have some piece of the network that has an internal state that changes over time. So how can we imagine that? We have this block that is the machine learning architecture, and we'll look inside this block in a moment. But we have this block, and this block receives an input. And with this input, this block does 2 things. It does one thing. It digests the input, and it changes its internal state. This is termed a hidden state that we represent here with H0. So it receives an input. It does some processing. It learns some nonlinear function of the input, and it puts out another output that we call H0, that we just store or we throw away. We don't need to keep it, but it now has changed its internal state. Then we give it the second input, so the second character of the poem, and it does something with it. It changes its internal state, and it returns a hidden state. And we repeat that until we've received the last character of the poem. And since the network has been able to change its internal state, it's able to learn about the complete poem by seeing one of the characters after the other. And at the end, we look at the hidden state, so at the output of this network block after the last character, and then we, for example, encode the information on the topic of this poem in this last character. And again, a brief aside, We are ramping up in complexity right now in this lecture very quickly. We're on an exponential rise of more complex concepts. So we started with just saying a neural network is a function. Now we're putting this function in a more complicated way so we can do interesting things with it. But you should never forget that all we're doing, in the end, we train with backpropagation and gradient descent. We just hide it in little boxes, and we don't think about the inner life anymore because we've understood how the gradient descent works. But this is just abstracting away the parts of the problem we don't want to think about. In the end, we can still train this exactly the way as we can train a fully connected network by comparing the output of the hidden node after the last input with the training target and calculating a loss function. It's all still, let's say, the same machinery underneath it. We're just doing more complicated things with it. So talking of more complicated things, I have here an example of a not absolutely state-of-the-art, but a reasonably popular classical architecture for this type of recurrent processing. This is called the LSTM, a long short-term memory. So I don't think it makes sense to go through the update rules of the LSTM in too much detail, but I just want to briefly sketch it so you have a feeling that when you see these abstract diagrams, you can always understand what's going on under the hood. You just need to look a bit closely. And in the end, it turns out to be a couple of networks that each of them have the function as David described it. So what we have is the input data coming in here. And the input data is copied and split into 4 copies. The arrow going up here, the arrow going up here, the arrow going up here, the arrow going up here. And before we do that, we concatenate it with the hidden state, so the internal state of the network from the previous layer. Then these boxes all represent, you can think of as a layer of the network that learns what to do with the data. And this LSTM structure has 3 basic operations. It has a include mask, a forget mask, and a new self state. So essentially what it does, it really learns, okay, from this new data, what do I want to keep? From the old data, what do I want to throw away? And how to combine that in an efficient way. As I said, you can stare at this diagram and we can discuss it afterward in more detail, but the basic idea is really that in the end, all these blocks are one layer of a neural network, and we're just structuring the connections and limiting ourselves to things that allow us to learn the storing of information and the throwing away of information. But this way, it takes the input data, it takes the previous self state, it combines everything, and the output is a new internal state of the network and the output that we report. And then at this point, the next input comes in, and what the network learns, similar to the geometrical filters that we had in the convolutional network, in such a language type processing network, the network learns functions, which part of the data, so which elements of an input should be kept and which elements of an input should be discarded. So it can slowly learn something about the whole poem. There is one downside of recurrent networks. There are 2 downsides. One is also present in language processing. One is particularly important for chat physics. Does somebody want to guess what the downside of this type of approach are? Sorry? Huh? I really don't understand the word, I think. Oh, I'm sorry. No, I can repeat the question again. So what's the downside of this way of treating data for chat physics or maybe also for language? What can you think that we can also see it in this recurrent issue? What do you think is the problem if we try to do that for a chat physics problem? Yes, please. Very good. The ordering is incredibly important because the last input the network sees will have an outsized impact on the final answer. So this means it will be very hard if we get to the end of this poem, the network might have forgotten what was in the beginning. And similarly, in chat physics, if we sort the chat by PT, we get to the very last particle, the lowest PT particle inside the chat, it might have forgotten about the structure of the high PT particles. So there is a direction of improving recurrent networks called transformers. I will talk about them if we have time later today, otherwise maybe tomorrow, that explicitly not only learns in order, but it learns in general. So any part can see all the text for its decision. So it learns that. That's very good. But in chat physics specifically, we have an even bigger problem with ordering, because ordering the 4 vectors per PT is, for the type of problem, not necessarily a good answer. There is nothing canonical about it, in the sense that it's not using any real symmetry of the data. I could order it by PT, but if I then have an additional soft emission, it swaps also back all the other particles. So maybe we can find a technique to represent the data that does not rely on an explicit ordering. If we have a type of input like a poem or any natural language text, then the ordering is a given. But the particles in the chat are actually unordered. So we can try to deal with that. And one answer to this is set-based networks, and Jesse has been briefly talked about that. So let's see if we can motivate ourselves. Or actually, let's take a breather and see if there are additional questions on recurrent architectures first. Yes? Oh yeah, sure. So sorry, this is a bit of an abstract diagram. I could have been a bit more explicit here. So what this is a network that learns essentially a new tensor that has the same size of this hidden cell state. So you can think if the hidden cell state. Sorry, this sounds very abstract. The hidden cell state, really think of a vector with 10 numbers. So this is a vector with 10 numbers, and the output of this network is also a vector with 10 numbers. And then you do element-wise multiplication of these 2 vectors. And well, if this vector had a 0 in a specific place, and you multiply the position in you multiply an element of the cell state vector with a 0, you've forgotten it. If it had a 1, this thing had a 1 in that place, you've kept it. If it has something in between, you've half forgotten and half remembered it. So this is really, this forget operation is a scalar multiplication between this vector and the cell state. The additional information adding is a scalar sum. So what this really does is, you have the cell state of 10 variables, you multiply it with something that zeroes out some stuff, and you add some new stuff to it. Very good question, thank you. Other questions? Yes, please.
One question about the jets. Could it be very advantageous to have the ordering? Because it tells me, let's say I order inverse in PT.
Mm-hmm.
And then this gives me the main focus on the very hardest departments. Or I could have some like additions which are harder in the beginning of the jet than at the end of the jet. So there could be advantages of having some order or some recurrent ordering in the data structure?
There could be. I think the answer is, it turns out in practice that there are architectures that don't rely on that explicit ordering, but that are still able to express everything in that sense that we care about. So you could play tricks with playing a chat forward and backward and then combining it, and this is actually a very good strategy to improve the performance. So for example, if you know you have something important in the beginning and the end, you run a recurrent network once forward, once backward, you combine it. You can do that, but it turns out that something we're going to talk about in a few moments is still able to learn exactly that patterns, but it's a bit more elegant in the way it treats the chat. But you're right. In principle, a recurrent architecture, especially if we introduce the concept of attention, is actually very powerful also for things that don't have a canonical ordering. It just turns out there are things that are even more powerful than that and don't rely on it. Okay, so we already complained about ordering. So this motivates, again, yet another way of looking at jet data. And this is the first time we're getting to something, I believe, that is, how should I say? It's actually fully representing the physics without any assumptions that we make to make it fit to an outside of physics learning problem. This is exciting. This is based on work actually by Jesse, so I'm very happy he didn't talk about it in the morning, or he only briefly mentioned it. So the observation is that there is no right ordering for the 4 vectors, and in general, for any fixed architecture, there's also something that we want to make sure that something works for arbitrary numbers of particles or events. Recurrent architectures do that, convolutions do it as well, fully connected fail this. And one way to think about our data is to think about all the 4 vectors just the way they are, as a point cloud. So essentially each 4 vector represents a point in 4D space. Okay, it's momentum space, whatever, it's still some 4D space. And the ordering of this point cloud is completely unimportant. This is just the way I write down my list of 4 vectors, but in the end, the physical object is just the distribution of momenta in space. So each point with their eta phi coordinates enter momentum, and we can very similarly see this to this image here. There's a propaganda image from a company developing modules for self-driving cars, because this is also the way these sensors in self-driving car, these LiDAR sensors, see the world, because they receive point cloud data, how far away all these points are, and maybe also something about the material properties. So again, this links to research outside of physics, but seeing the representation of the momenta in the jet just as a cloud of momenta that live in some geometrical directions is the first thing that really covers all the information of the physics without trying to shoehorning it into something that is not really there. So point clouds are nice from the physics point of view, but this raises the question how we can process something that has this type of structure, again, with the neural network. Because if we have point clouds in abstract space, how can we deal with that? The answer for point clouds is surprisingly simple. And the key observation here is the sum. The operation of summing stuff up is permutation invariant. It's an incredibly trivial statement. A plus B is B plus A. This is all that this is saying. But this is all we need to solve the problem that we have in the following way. We can structure our network into 2 parts. The first network sees individual particles. So we have one network that sees one particle as an input and outputs some, it's called here a latent space, so some set of features. So each network, so this network sees a particle as an input and produces 5 output numbers. And we can apply, this is in this picture, this is the network phi. And we can apply the same network, so not only the same architecture, important, but the same weights to all the particles. So we said in this top tagging problem, we have 200 particles as inputs. So we apply this network with the same weights to all these 200 particles. And it learns a latent space representation for all these 200 particles. If we say the latent space is 5-dimensional, then we have 200 times 5 features at this point. Now we use this amazing property of the sum that I just mentioned, namely that it's permutation invariant, and we just sum up the latent space representation of all these particles. So we turn 200 times 5 numbers into just 5 numbers by summing over the direction of 200 particles in each case. So now we have what we can call a global latent space representation of the particle. And we can take this as an input to a second network. This is very simple and very powerful. And if we want to write it down as an equation, we have 2 networks, psi and f. And in the way that we were representing them yesterday, the network psi and the network f both would have a set of trainable parameters. And then we have a final output. And again, we can do all these tricks that we discussed so far. training via gradient descent by optimizing a loss function. Since this is just a differentiable function of the two networks, we can use all this machinery without any changes. But again, we just found a way to structure the individual networks in such a way that they explicitly respect this permutation invariance of the input particles that we know that our physics data, if we're talking about jets, has. You can notice, I like deep sets. I think this is a very elegant architecture. But I don't want to oversell it in the sense that we assume here permutation invariance of the inputs. In many cases, the jet tagging problems I'm interested about, this is a true assumption. If you're working on some phenomenological problem and your inputs are explicitly one particle is a top and one particle is a lepton in some final state that you want to do something, this breaks permutation invariance. So there are probably better things to do in that case than a completely symmetric network. But whenever your inputs live in some space and are permutation invariant, this is a very nice way of looking at it. It's not as powerful as some of the architectures I'll talk in a moment, but it's a very good starting point. There is also one thing I wrote down here. When is a convolution a set? This is an important observation. We've introduced convolutional architectures as something that lives in image space, as something that we do when the data is an image. You could also imagine applying a convolutional architecture just to a list of inputs and shaping your convolutional kernel in such a way that it sees one particle at a time. This way, plus a bit of pooling, this way you could actually write down such a network structure very simply by using the tools that the convolutional architecture gives you. If it's not immediately clear, maybe it makes sense to think about it for a bit, because you can learn a bit about convolutions and how to write it down if you think how you write down a particle flow network as a convolution. Okay. Quick breather for questions again. I'm not sure if everybody is exhausted or if you're still coming along. Okay, people are looking lively. Very good. Now, we still have a bit ahead of us. I'll be going through that one a bit more quickly because it's not as powerful as the next thing we see, but it's a nice direction. I've started this whole discussion of architectures by saying this is one of the ways that physicists actually can contribute to how data is processed by machine learning algorithm. And we looked at a few things where we actually take approaches from outside of physics and try to say, oh, we can fit our physics data into it, even if it comes with a bit of tension at some point. We found one technique that works quite well for physics data, but maybe that's not as expressive as it could be. There is a trend of developing machine learning algorithms that explicitly try to make use of some properties of the physics. And I just quickly show this approach here. So one thing we tried a while ago was actually to say, okay, we know that our data is 4 vectors, so why don't we have a network that consists of 2 components? A first component that learns linear combinations of the 4 vectors, so the weights in the network correspond to the coefficients in the linear combinations of the input, and the second layer that tries to project some Lorentz invariant quantities out of these 4 vectors, or slightly violating Lorentz invariant. And then again, thinking of these 2 steps as a feature extractor, following up with a fully connected layer for a final output. So a bit more explicitly working with 4 vectors. This is just a structure. We don't need them in that much detail. But so even though that this is not so powerful, there is a certain amount of developments going in this direction. Another beautiful way is saying, okay, we have a list of input vectors. We have a network that learns linear combinations, and we call some of them particles and some of them rest frames. And then we do an explicit Lorentz boost of all the particles into all the rest frames, then extract features from there and feed it to a neural network. So if you have some physical property that you want your network to learn, the only trick is to make sure that all the operations you write down here don't spoil the differentiability of the loss function. As long as you only do things like calculating a Lorentz boost and making sure that everything that you do is done in a differentiable way, you can get away with doing quite a bit of physics and calculations inside the network. And especially the programming language that Sungak is teaching you for representing these architectures, PyTorch, gives you great flexibility in encoding these things. So if you want to try to combine physics and machine learning, these are actually some nice starting points. Okay, we're good in time. So as a kind of the logical endpoint of everything we've talked about so far, let's see if we can yeah. So you put me in a difficult position because overall I like this architecture and it was written by some friends, but I don't like the feature extraction at all. So I was hoping that I get by with it, but you spotted it. So think of this as particles boosted into, sorry, it's not all particles in all rest frame. It's the first particle in the first rest frame, the second particle in the second rest frame, and so on. You're right. Otherwise the numbers don't work out because then we have m, which is the number of particles, times 4, which is the number of features per particle. You're right about that. And the feature extraction is really, all of these things here are 4 vectors. So the feature extraction you can do is you calculate the mass of each 4 vector, for example. Or you calculate the pairwise invariant masses and stuff like that.
So this feature is created by hand?
Well, it's hard-coded, writing down a list of the physics properties of 4 vectors you want to write out at this point. This is exactly, I think this is the weak point of this architecture. If I would do it, I would put a deep set network on top of that. But exactly, here the feature extraction is explicitly extracting physical features. So the motivation for this architecture was more to learn the particles and the rest frame, and then here stay very physics informed. You could replace this manual, well, it's not manual in the sense that it's still all integrated as part of the network, and it's able to differentiate and to backpropagate through it, but it's manual in the sense that you, as the developer, write down the list of features that you want to extract here. Agreed? You can do this in a more deep learning paradigm way, but you can also do it this way, and it also works, but good, well spotted. Okay, now let's combine a few of the requirements we had for network architectures when we set out to do that. Because even though we discarded images, because it's very difficult to represent arbitrary resolution data as an image, they had one nice property. Locality, meaning that stuff that lives close together in geometrical space automatically got treated together by the machine learning architecture. However, images had this big disadvantage that they were scaling badly, so there is also this development of permutation invariant things that respects the permutation symmetry of 4 vectors. And one very powerful answer to combine these 2 intellectual threads are graphs. And there is a huge explosion in graph-based or in geometric machine learning, as it's called, based models, both inside particle physics but also in the outside world. And I just give here a very brief glimpse into that world. But if you're excited about this, there's a review paper actually by some physicists and some Google machine learning people that tries to give an overview of all the developments of graph machine learning in particle physics. So for our purposes, let's try to do something very simple. And we encode each particle, so each 4 vector, we encode as a node in this graph. And we can build a graph out of a particle by doing some clustering in the geometrical space. So we assume that for all these particles, we have the pt eta phi coordinates. So we can do a k nearest neighbor clustering in eta phi space, and then say we connect each particle with its 5 nearest neighbors in eta phi space, and that way build the graph. This produces a fairly nice graph that accurately represents the jet. It's not 100% elegant because, again, we need to put out some geometric clustering that's not directly inside the physics, but it has the advantage that we have then built something that is easily represents arbitrary resolution because we only have as many nodes as particles, but we've still encoded some sense of locality by the fact that we can do this, this geometric clustering in this nearest neighbor clustering in geometric space. And in general, I think this is, again, like an evolution of the statement I've been making. So in classical approaches, our mental energy went into coming up with high-level observables. In many machine learning architectures, the intellectual energy goes into defining the architecture. We've now arrived in graph land, where the graph architecture is actually quite powerful, but you need to think about how to best represent your physics problem as a graph that allows meaningful work with it. And one nice thing about this is that whenever you have point cloud data, so whenever we have data embedded in some geometric space, something where we can define a distance measure, then we can just run a clustering system in the distance measure and use this to construct a graph. We can also use data that naturally comes as a graph. And again, I'm under the impression that this is a slightly theory-heavy audience, so I just throw in decay sequences here. So I have something like a Pusia decay chain, where you have a sequential decays of particles. This is naturally a graph. Well, it's naturally a tree, but a tree is a type of graph, so can get away with it.
I have a question.
Sure.
So in this application to the particle physics, you mentioned about enterprise plane.
Yeah.
Then you need to define the metric, the distance, right?
Yeah.
So the one easy thing is data R.
Yeah.
Is there any distance except of data R?
Okay. So I think I'm pretty sure that the papers that started this whole business use delta R. You could also, and other people have been doing that, you could also represent XYZ space and cluster in XYZ space. This is useful, for example, if you have hits in the colorimeter where you really care about the geometrical situation. However, let's wait a moment until we see how graph networks work, because one nice feature of the graphs, I can already maybe spoil it here, is that while we start in some geometric space, what the graph learns is features for the nodes, and you can at each step recluster the nodes, and thereby you can think of the graph learns the best space to represent the data in. So even if you start with the bad representation, the graph can figure it out. If you start with a good representation, then it has an easier time, but in principle the architecture learns a way of seeing which stuff belongs together.
Do these procedures depend on the metric?
It depends on the metric in the initial geometric space that you start from. After the second layer, you always use the Euclidean metric in feature space. It's not physical, but again, it's one of the things you just get away with because it's very hard to define a physically meaningful lecture for this metric for these abstract vectors. So you just use Euclidean metric and let the graph learn a good representation so that the Euclidean metric makes sense. You can think of it that way. Okay, so, and again, just saying it one more time, graphs are a very large and evolving topic, and I'm just showing one relatively early and relatively easy to understand approach. But if you're interested in applying them, there's a much larger literature out there for you to sample. But we can start with this. So we can pick out one node in the graph. You can think of, we pick out one node here. This could be the node C, and we see the node C has 1, 2, 3, 4 neighbors. So if, well, pick the bad node because this one has 5 neighbors, but you can really think, well, this center thing here is the node we're currently talking about, and all these other nodes are its neighbors. And when we process the graph, what we do is we process it simultaneously node by node, similarly in the way that we've been applying a convolutional filter to the input image when working with chat images. And the edge operation consists of 2 steps. The first one, and you can think of this, if you remember how the deep set architecture works, you can think of this very similar to the deep set architecture. So we first have a network that takes as an input the central node, so the features of the node in the center, and the features of its neighbor. So for example, xi1, this feature here. So this is a network that has 2 slots for inputs. So for example, if our inputs have 5 features, so this would have altogether 10 features. And h of theta This is just a neural network. And we apply this to all of the 5 neighbors. And then we apply this block function. This is just a way of displaying an arbitrary aggregation function. So some function that is permutation invariant under its inputs. In the deep set architecture, we talked about sums. Sums are obviously invariant under the order of input. The maximum operation is also invariant under the inputs. It doesn't matter in which order you give your inputs, you just care about the maximum. So there is actually a larger family of aggregation functions you could use. But for simplicity, when you're thinking about what it's doing, you can think of using the sum. So we apply the sum to the output of this network, and this is just as we applied the sum to collect the features after the latent space of the deep sets architecture. Yes? Yes, but that doesn't mean that you could use others and learn more quickly. You know, the sum is universal. Yeah, the sum is universal, but in practice sometimes you know, it's the same with neural networks. In principle, a 1-layer infinitely deep network is a universal approximator. Still, we're doing deep networks because we hope to learn better. But you're right, the sum is universal, yes. So we do a second, the output of this step is then a new value for the node I. This is xi prime. And this way, we've now updated our node. So you can think of the output of each of these networks. You see the output of this H5. You can think of this edge update, and it goes to the central node, Hi. You can also do other, you can do also many kinds of other architectures, like, for example, taking explicitly into account edge features and so on. But in principle, just what we need to do is we need to find a network that can take a central node and a neighboring node as an input and do something useful with it. In this specific example, we're looking at something that takes the central node and the difference between the neighbor and the central node. But you're not limited to that. So that's essentially a choice similar to a hyperparameter choice.
Can I ask a really stupid question?
Sure.
This is super stupid. This aggregation function looks like pooling to me.
Like what? Like pooling?
Pooling in CNN. They have a similar.
I don't think it's a stupid question at all. Well, with the pooling operation, you're aggregating over geometrical neighbors to get an answer. With this, you're also aggregating over geometrical neighborhood in some. Yes, I think it's good to say it fulfills a similar role. I think that's a fair statement.
It was not stupid.
Yeah, not at all. Okay, so we've now figured out the way to update a node in such a way that takes into account its neighborhood in a way that is permutation invariant, because, well, the individual operations are permutation invariant, and we can put that together. So I'm not going to show you how you turn it into a complete network, because it's, again, the same. We have an operation. Now we can do it many times in parallel. We can do it a couple of times after each other, just as we did with the convolutional architecture. And this allows us to turn a graph-based convolution into a deeper graph-based model. So again, it's a very similar structure. I'm looking at the clock, and I'm more or less out of time now, I think. So let's come to a conclusion for now, and I think that's actually a good starting point for tomorrow. I've talked now 3 hours about different architectures. And as I said in the very beginning, all of them were tested on the same data set and represented in this diagram. So on the horizontal axis, we have the signal efficiency, saying which fraction of top quarks are correctly identified as top quarks. On the vertical axis is 1 over the background rejection, saying which inverse fraction of QCD jets did we mistake for a given threshold. So you can think of training the network. For each input, the network gives 1 output value, the probability the network thinks that this is a top quark, and then you can cut on this output tighter and tighter to have a lower and lower signal efficiency. If we don't cut on the output distribution at all, and if we accept everything, we have 100% signal efficiency, but we also don't reject any background. And then if we go tighter and tighter, the signal efficiency goes down, but the fraction of background we reject goes even higher up. So this is a classical ROC curve that is one of the main ways of showing performance in a machine learning application. And if we now compare all these different lines, well, the key lessons are the classical approach. So a fully connected network that takes some n subjedinous variables and the mass as an input. This is the orange dotted line. So it has some non-trivial performance, but it's also not doing very good. And this thick band of stuff here, that's all the deep network architectures. The best performance in this case comes from a graph-based approach. This is the particle net. This is the blue line. Whereas you also get very close, for example, with the well-constructed deep image-based architecture. That's the rest next, the green dotted line. In some sense, I would be very careful in drawing the conclusion that one approach is much better than another one just from this. So I think for me, the main message is this is really a factor 2 improvement or factor 2 to 3 improvement from deep learning, from shallow machine learning going to deep learning. And then it depends again how well you optimize into specific tools of the architecture. But this is a very strong statement in favor of.
Can I ask another question?
Sure.
Okay. So this article is based on the almost infinite number of the statistics, kind of.
I'm looking doubtful because 1.2 million training examples is it's good enough. It's not really large compared to what we actually have available inside the experiments for the actual application. But,
no, but in the end of the game, you may have 100 samples or 100 events, right? Then how this, I think then for the 100 test samples,
yeah.
maybe the best one would be the simplest network, not the complicated.
Well, but you don't care about the statistics of your test sample. As long as the training statistics is large enough, the better trained network will always do better on a smaller test sample as well. You're not training on the test sample. You're training, for example, on Monte Carlo simulation where you do have 1 million events available. But you're absolutely right. If you're in a situation, so in my previous life, I was doing an analysis searching for TTH, so a pair production of top quark and the Higgs boson. And TTH, if you go into a region of phase space where it becomes interesting, the statistics is so limited that you hardly can get out anything from Monte Carlo simulation. And in these applications, we literally had 10 events available for deep network training. And then you can't do anything fancy. So you're right, these situations exist. Okay. Okay. So there's one or two other statements I want to make here. So the first one is the strongest performance we got from the graph nets here. But there is a closed net, we already said that. The next observation is a practical observation. If we compare the performance of a network from a single training to the performance of training the network multiple times with the same initial parameters and just taking the median output, so instead of training one network, you train the same network 10 times, and you take the median of the 10, it actually improves your performance. So there is some amount of averaging that gives you a free performance boost. This is nothing else than the underlying principle of boosted decision trees, just in a much simpler way. So you can always gain a bit of performance with ensembling because it stabilizes the result. The other observation is that there is a very limited gain by, we can take the output of all these architectures and use them as the input to train a fully connected network. So we could be wild and just consider all these things as feature extractors for one more network. It turns out this adds a bit performance, but not much on top. So apparently, let's say they all more or less seem to extract the same information in the sense that makes it difficult to combine them in a meaningful way. So they're not orthogonal. This does not mean that there couldn't be more information out there, but at least this space did not cover it. And I think the last statement here is looking at the number of trainable parameters of the architecture. So there is some things that have many parameters and perform well. There's also some things like the ResNext, for example. There's also some things like the Lorentz boost network that has many parameters and does not perform so well. So just pure parameter counting does not automatically give more performance. It needs to be encoded in a meaningful architecture. And I think this is a very good point to close. So we used the single top tagging problem as a very useful benchmark, and we now made a large scroll through the landscape of machine learning for top tagging, and I think there is some very interesting physics insight that can go into designing these networks. However, and I think this also addresses again the point that you raised, and I think that's very, very important, such a study has obvious limitations. And for a practical application of these tools, many other considerations are very important. How fast can we actually run this, for example, in an experiment in production? How stable are these with respect to experimental conditions, with respect to outlier inputs, with respect to changing calibration factors? How much data and effort do we need to train, and so on. So there's a long list of issues for practical use that are not addressed in the study, but the overall message that deep learning adds capacity, and that by thinking about the architecture in a smart way, we can have nice improvements in performance, I think do hold relatively strongly. And I think this is a good endpoint. Thank you.
Yeah, thanks for the nice lecture. Any questions?
I have a question regarding that, the one that we have this data put on, and because we wanted to impose the permutation invariance, we used sum. And there are like other functions which are permutation invariance, like a sum of all pairwise product or sum of all like triplewise products like that. And why are not using them like aside the sum?
I think David also was alluding to that. So there is one theorem that, if I remember correctly, you can also correct me, but that the sum is able to represent that the sum, the structure that is encoded in the deep sets with the sum is in principle able to also learn all these other versions of functions, so that it should be able to learn any possible function. But again, in practice, this is, the one thing is theory, the other thing is trying to get best performance on a particular problem that you care about. And in practice, you can play with saying, oh, I add, for example, I add the maximum in addition to the sum. I add the variance in addition to the sum, or what, as you said, the sum of the products. You can play all of these tricks, and in practice, it might give you a performance boost. Because just because something can learn the whole structure does not mean it will do it in an efficient way. This is an aspect of hyperparameter optimization.
Yeah, I think the theorem is that sufficiently with arbitrary f and phi being the pointer and
Yeah.
any permutation very function can be represented with a certain sum. Like the pairwise example you gave, you could write that as like x1, the sum of all the x's squared minus the sum of all the x squared.
Thanks.
Is CM, or I remember papers by, I think, CMS, where you have taggers already for tops, W's, Z's, and Higgses, which are, I think, machine learning based. Are they, or which neural networks are they based on?
Now I need to think carefully what we put out. Let me phrase it differently. The default architecture these days is graphs. I'm not sure if we've published top tagging with graphs as a paper, and I think there was a big top tagging overview paper by CMS that was before graphs. But by now it has largely moved to a graph-based architecture. So the main workhorse before graphs was, this was the reason for this one side remark I gave here. When is a convolution set? Because this was for a while the main way of CMS, way of doing things, is doing a 1D convolution in such a way that it was essentially acting very similar to a deep set-based approach. But by now everything is being colonized by graphs or attention-based graphs that I'll talk about tomorrow briefly. David?
So your very comprehensive summary of the landscape paper is from 2018, I guess? And is it true that I think like Huiling and his collaborators have gone beyond
There is some material beyond the landscape that we will touch upon tomorrow.
But it's true, right? There's no
Yes.
caveats. They really did go beyond.
Yes.
Yeah.
Well, I wanted to read that before I talk about it again because I think they have some results on other data sets, but there's at least one result also on the landscape paper that further improves the performance.
Okay.
But like there is 1 or 2 results on other top-taking data sets where they even see larger improvements, but not everything is reported on the landscape data set.
I see. Actually, so that if they use like more tops to train on, then
Exactly.
it would be not apples to apples anymore.
Well, you can still say that if you have a very expressive architecture, you compare it to another architecture on a larger data set, and you see that it makes even more out of it. So
Yeah.
I think it's a useful study to do, but it does not mean that it's only more powerful because it is more expressive. It's also more powerful because in that comparison it had more data.
Yeah. Okay.
But if you compare it to something less powerful on the same amount of data, it's still a valid comparison for them to do.
And actually, is it also true that the particle net is extremely expensive to train?
Yes.
I see. So that's a downside.
So I hint at this at ease of training, but you're right, maybe we should be explicit about that. So the graph-based architectures that follow this model, maybe even better the previous page, where we say we do some K and N clustering in the data space and then repeat the K and N clustering in the latent space. The clustering step is very expensive.
Oh.
The graph processing is very similar to a convolutional network. This is all fast. But changing the clustering leaves, let's say, the land you want to be in, and that becomes slow.
Okay, so we are running out of time. So unfortunately, we only have like 20 minutes for coffee break. So next lecture will start at 3:15. Okay, thanks again.
Thank you.